Welcome to a lesson with Dr. Powell. In this video, we're going to take a look at a problem that asks us to find a little differential, a little change in the variable z, given that we know these other differentials, dx is 0.8 and dy is 0.7. These are like changes, little tiny changes of these variables. Now, imagine, so we have multiple variables going on, but to simplify things for ourselves, let's just imagine that every one of these variables depends on something, the same thing, perhaps. Maybe everything depends on some parameter t, like for a related rates question, like t or whatever. Then x, y, and z are going to be functions of t. And then we're looking at a particular moment for a particular value of that parameter t. So t is going to be equal to something very specific at a particular instant, and these are the outputs there. But in order to relate these differentials, we're going to have to think of t as being variable. Just we'll use this information. We don't even know what t is or what it's going to be set to, but we do know what the output is let's just call it a. The output is at this particular moment, if t is time or whatever, and we can use that. We can plug these guys in later when we need them, and we'll see. It's a lot like a related rates question. Look at my videos on related rates. I have some ideas there on some of those, how this works. But in this video, I'm going to show how the boxing rule can actually make life easier for related rates questions, as well as differentials, differential questions, funny. Actually, you can use them for implicit differentiation as well. Boxing is a very useful technique for implicit differentiation. It's also a nice technique for differential approximation, which is what this question is, as well as related rates. But really, all of these things can be thought of as one and the same, really, especially what we're doing right now. We're thinking of x, y, and z as being functions of the same thing. Okay. Well, maybe we should understand what these guys mean right here, dx, dy, and dz. If we were to draw a function, or a picture of the function x as a function of time of t, so, x is going to be a function itself with respect to t. So if we were to graph x as a function, it's kind of funny thinking of the variable as a function, but yeah, okay, variable is a function of time, so, and in particular, at a particular moment, this moment, t equals a, there is a tangent line. Now, the rise, you have a rise over run. So the rise of the tangent line is dx for a particular run dt. Now, what if we made the run dt the same for the graph of x of t and the graph of y of t for the tangent line? So maybe this dt is the exact same, and then this would be our d, then we're going to get a dy out of that. And then we're going to use the exact same dt on the graph of z, whatever that is. So z of t, and here's a tangent line at the point t equals a, tangent line, and so then you can kind of think, okay, dz, dt, use the exact same run. So if using exact same run on all of these, and we know what the rise is of x here and the rise is here for y, we should be able to figure out this guy, okay? That's kind of the goal, figuring out what that is. Now, albeit, this may not be exactly there are other interpretations and ways of seeing this, but in a first semester calculus class, if we have different variables like this, it's nice to relate them to the same thing. So you can kind of have a picture or a sense for what the variables, the differential symbols dz mean with respect to dy and dx. Now, maybe in a multivariable calculus course, you could relate dx and dz, like dz, dx, and dy together in a nice way, so you actually have a picture of a plane that relates these guys together. But if you want a picture for a single variable calculus course, this is convenient. There's a single variable t that we're going to be using here. Okay, all right. And it's a great start, a great place to go to see different relationships and how they can go. Just keep in mind that, yeah, maybe there's another geometric simple way of seeing this as well. But if we want to do one thing at a time, just remember that these guys tangentially give us this kind of relationship here. See, what we're going to do is we can find a relationship between dx dt, dy dt, and dz dt. And as long as this dt is the exact same, okay, for all of these, this is going to be a linear relationship. I mean, it's going to be like something like this. A times this guy plus b times this guy is going to be equal to something like c times this guy. Now, in such a relationship like this, and if dt is the same overall, okay, and we're going to be using instantaneously at this moment that dx dt, the derivative, is actually going to be equal to this ratio of dx to dt, rise over run, of the tangent line, by the way. Okay, that's where differential symbols come in. It represents of the tangent line, that ratio. Then what you could do to both sides, and this is perfectly legal, assuming that dt is some fixed value that's not 0, and so these make sense, you could multiply this whole equation by dt, and then they just disappear. And then you have a relationship between these guys, dx, dy, dz. Okay, so dx represents kind of a derivative type tangential little approximation to the change of x. It's not change of x, but it's a change of x on the tangent line of x. You could think of it that way if you like. Okay, so but it has a relationship between this little thing. You can think of it as something that approximates the change of x. So if the change of x is about 0.8, the change of y is about 0.7, then about what is the change of z? That's really what we're asking here, but we can do that with these tangential relationships. So we can think dx, dy, dz. We have an equation that relates these guys together, this dx, this dy, this dz together. Awesome. Okay, but first, stepping ahead, we got to figure out what this relationship is. How do we get it? Like I said, boxing will come to the rescue. How do we do that? Okay, so we're going to think of this equation. We're going to take a derivative of both sides with respect to t, all right? Where x is a chunk, y is a chunk, z is a chunk. You can think of them as boxes, all right? When x takes the stage, x is a box. Everything outside of it is going to be considered constant. So if you take the derivative of this side, then, in such a case, then this would be like a constant. Then it would be like constant over x, or constant times x to the negative 1. Oh, so really it's kind of like y x to the negative 1. Just taking the derivative of that, well, y is considered constant. Negative 1 would come up to the front. So negative y x to the negative 2, but at the end of a boxing situation, you multiply by the derivative of the box with respect to what you're taking derivative to, t, so dx dt. Okay, now keep in mind, I'll just box this right here, because, okay, this scenario, oh, that's an x, sorry. I don't know why that came out. Okay, so this is with respect to x when x takes the stage as a box, but we add to that what happens when y takes the stage. When y takes the stage, then this is kind of like x to the negative 1 is like a constant. So it's just constant times y. And the derivative is just going to be the constant. It's just 1 over x is the derivative of that side with respect when y takes the stage. But then at the end of the boxing, you put down a derivative of what was boxed, dy dt. And then you add to that, okay, what happens with z? So with z, notice this part is constant. You just have phi to the z. Derivative of phi to the z is ln of 5 times phi to the z, but remember, z takes the stage, but at the end of this boxing, you multiply by the derivative of the box, dz dt, with respect to what you're taking derivative, which is t. And so this whole side is effectively the derivative of the left part, and then is equal to 0. Now notice how this is so nice, because you only see one dx dt occurring, one dy dt occurring, one dz dt occurring, times something, times something, times something. And at this particular moment, now is the time to plug these guys in. Plug those guys in, and you have a relationship between dx dt, dy dt, dz dt. These guys will just be numbers. And in particular, we know what we can do is we can multiply this whole side by dt. dt's are gone. And we have times dx, times dy, times dz. Great. So now we have a relation between dx, dy, and dz. We can plug in things. For dx is 0.8. For dy it's 0.7. And I didn't give units here. But and then dz, well, we can, whatever units they are, we'll figure it out, I guess. And dz will is what we're solving for. This constant right here, I guess we can plug these numbers in. Y is 1, x is -3, but you're squaring it and taking reciprocals because the -2 power. So 1/9, -1/9 is that constant, so -1/9, because you have y is 1, x is -3, and squared, so it's just +9, but then you have a negative out front from here. So -1/9. Then 1 over x, that's -1/3 right there. And then this ln of 5 to the z. So 5 to the z is a fifth. So it's a fifth times ln of 5, or ln of fifth root 5, or however you want to think about it. But using the property logs, but maybe I'll just write it this way. Plus, so 5, let's see, is that right? 5 to the z, 5 to the -1, so which is a fifth? ln of 5. Okay, something like that. And that's equal to 0. Notice how we could solve quickly for dz now. So approximation, right? Worked. And we could have thought of this as dx dt, dy dt, and dz dt. We have a related rates question. And so we could solve for dz dt then. So notice how it's pretty much the same type of idea. And what saved the day? Boxing. Boxing was very nice. Now, in a more advanced course, actually, boxing has another name. And it's a very nice way of relating dx, dy's, and dz's together, but why not talk about it right now? It's a fairly nice way of looking at it, and naming it as boxing and how it's explained in this particular way keeps it simple, and so it actually is digestible and we can work with it. Okay, so now what about in something like this? Okay, so this is the same type of question, but maybe we'll go through it a little bit more quickly. But also, you see this percentage. Sometimes things are given in terms of percentages. 2.5% of x. So maybe you say, like, x is changing by 2.5%. What in the world does that mean? Well, of what it is currently, okay? Its current value is 3 at this moment in time. So basically, you just take 2.5% of 3, right? So 2.5% is half of 5%. 5% is a 20th, so it's a 40th. Whatever you want to think about it that way. Is that right? Yeah, so 40th. So we could think of, so in particular, dx is just a 40th, 2.5%, that's just 0.025 times the current value of 3. And that's just, it's just code for what it is. Instead of giving a number, sometimes a percentage is given. You might see that sometime. But anyways, so dx, maybe I'll just rewrite it as 3 over 40. And maybe we're looking for what dy is. Okay, how do we find this? We're going to, think of it kind of as a related rates type thing with the dx dt, a dy dt, and kind of proceed that way. But instead, at the end of every boxing, if we just multiply by dx, dy, we're good. So we have x boxing first. So derivative, and we're just going to split this up. So on this side versus this side. On this side, derivative is just 0. That's nice. On this side, if the x's take the stage, then this y squared is a constant here. It's just constant times x. Derivative of that part is just y squared, because it's the constant times x. Plus this is x to the negative 1 using the power rule. Let's see, we're going to get, then we will get, this, and we'll say, so we have y squared minus x to the negative 2 times, so next negative 2, but then, okay, so that's the derivative with x takes the stage, but at the end of that, you multiply by the derivative of the box. So dx dt, but instead, we're going to do dx. Because as in the last example, dt's will go away when you can kind of fix them as the same thing across. Then you're relating your changes to each other. So then you add to that what happens with when y's take the stage. So really, this guy's constant. It's just y squared times a constant x. So derivative of that is just be 2xy if y is the variable, but then you multiply by dy dt, but we'll just do dy. So then the other side is just a 0. Okay, very nice. We can write dx and dy together at this particular moment when x is 3, y is 2. When x is 3, this is x to the negative 2, so that would be 1/9. And y is 2, so that's 4 minus the 9th. Dx is going to be 3 over 40 plus, let's see, 2xy, so that's 6 times 2, that's 12, times dy. So we can figure out what dy is in this particular situation by just working out that arithmetic. And we'll end the video here. Thanks for watching.